Hi. So, look, what we are going to take up this week is repetition of integration, because integrals are another subject, another tool that we are going to be using very often in our future considerations of different economic problems. Okay, and let's start with indefinite integrals. Okay, so the main formula, I will be just replacing x with t. All the formulas we already learned in mathematics, so let me just refresh the most important ones. So, integral of t to the power of n dt. As you notice, the only thing that I've changed here is actually x to t, is t to the power n plus 1 over n plus 1 plus c. But of course, right away here, we need to notice that n must be different than negative 1. Of course, I hope you remember, for 1 over t, we have a special formula, logarithmic formula. Okay, and the second thing before we start is we need to notice that integral of f of t plus minus g of t dt is the same as integral f of t dt plus integral g of t dt. Okay, so now let's try a couple of examples on how we integrate. What is integral of 0? Well, what gives us a derivative 0? A constant c. Then, what is integral of 1? What gives us in derivative 1? Well, x. Normally, at this time, this would be t, but of course plus c. And what is integral of t dt? Well, now we just need to use the formula, and this will be t squared over 2 plus c. I hope you're starting to remember it better and better. Okay, then we've got an integral to t to the power of 3, negative 3, dt would be t to the power of negative 2 over negative 2 plus c, or negative 1 over 2t squared plus c. Okay, so those are the most basic formulas. Maybe we should add one more here to this collection of the two formulas. That integral of k f of t dt is the same as k integral f of t dt. So remember, where k is of course constant, and remember we can always take constant out of the integral. But of course, look, in this subject we are dealing with time, and when we are dealing with time, the most useful formulas for us are those associated with exponential, natural exponential functions and logarithms. So, first, we need to remember that integral of e to the power of t is e to the power of t plus c. And similarly, integral of 1 over t dt is ln absolute value of t plus c. But remember that in our economic application, t is time when time cannot be negative, unless you treat something as a point in time and then you count backwards. But usually we will not need this absolute value of t. Okay, then we've got the formula that f prime of t times e to the power f of t to differentiate this expression, remember that we need to use this formula. So, when we differentiate the function, we take the derivative and put it up front. So what we want to have here is the derivative of the exponent. Derivative of the exponent here is 2t. Right? So, in order to obtain 2t, what do I need to do? Well, I need to take out of the integral 1 over 2. Right? And now I can use the formula, and I get that this is 1 over 2 e to t squared plus 1 plus c. Okay, and of course we need the more general formula for logarithms, and we get that this is f prime of t over f of t dt is the same as f is equal to natural logarithm f of t plus c. Okay, again, let's make an example over here. Let's just say that we've got integral of 12t plus 4 divided by 3t squared plus 2t dt. Well, again, what I want to have is to have derivative of this function over here. But derivative of this function is 6t plus 2. So, what I need to take out of the numerator, I need to take 2. And then I get 6t plus 2 over 3t squared plus 2t dt. And this is of course equal to 2 ln absolute value 3t squared minus plus 2t plus c. Okay, and look, those are basically all the basic rules that we are going to use in this class. There is unfortunately one more rule that I need to repeat with you that you probably don't like that much, and this rule is integration by substitution. Good information is that in this class we will not use integration by parts, and because we will not use integration by parts, I'm not going to force you to repeat this. Okay, so in case of integration by substitution, we've got the integral of f u du d t dt is the same as because those two cancel each other out. Integral of f u d u, and this is equal to f of u plus c. Okay, this is the rule, but let me show you how to use it. Okay, so look, here we have a rather troubling expression, integral of 6t squared t to the power of 3 plus 1 to the power 99 dt. Well, clearly this is a complicated case unless we use integration by substitution. Just like before, we need to assume that u is some part of this function so that derivative of u will be over here. And clearly in this case, the best candidate for u is t cubed plus 1. Then du dt is given by 3t squared. So we want to have this 3t squared over here. What do we need to do? Again, we need to take something out. In our case, this will be 2. So we've got t squared t to the power of 3 plus 1 to the power 99. And look, now all all we've got to do is to, dt. Substitute. We've got 2 integral sign du dt times u to the power 99 dt. Those two cancel each other out, and they always will. So we end up with u to the power 99 du. And this integral is extremely easy to calculate because we get that this is 2 times u to the power 100 divided by 100 plus c. Now of course those two cancel each other out and we get 50 in the denominator. Okay, now in the last step we of course need to substitute back for u and we get the final result that this integral is equal to t cubed plus 1 to the power 100 over 50 plus c. And this is how we use integration by substitution. Okay, and I think this is enough when it comes to the repetition of indefinite integrals. The next thing we need to repeat are definite integrals. Look, definite integrals is something that we use in order to calculate the area below the function. And look, in the definite integral with lower limit a and upper limit of integration b out of f of t dt is given by f of t. So once we calculate indefinite integral, we just put it here and we put a and b over here. And finally, to calculate the area, we just substitute the values b first and then a second. Okay, again, let's use an example. Very simple. So look, I want to know what is the area below the function y equals t squared between 0 and 1. In order to find that, I need to calculate integral from 0 to 1 out of t squared dt. Right? So, integral of this is simply t to the power of 3 over 3. I got 0 right here. Now I just substitute and I get that this is 1 over 3 minus 0, which is equal to 1 over 3. Now, usually we finish this with the graph, so why not now? And we've just found that this area below the function y equals t squared between 0 and 1 over here is equal to 1/3. Okay, I don't think that was that complicated. And actually, this leads us to one last thing we need to repeat before we can move on with the economic examples. And this last thing are improper integrals. Improper integrals are the integrals where we have either infinite limit of integration or value of the integrand is going for infinity as we approach some point. For us, only one case is relevant. If we have a situation like this, because of course, look, now with economic problems, we don't need negative infinity because infinity will be our time. So what we want to deal with is the case like that. So we want to find area below this function from a to infinity. How do we do it? Well, we start the way we did it with with proper integrals. So we first find definite, indefinite integral, and here we write a, and b goes for infinity. Because of course we cannot substitute infinity. But when something is going for infinity, of course we just need to calculate the limits. And then we subtract f of a. Once we've calculated this, we will be able to find the area below some function from some point to infinity. Okay, again, let's try some examples. So look, I want to know what is the area below function y equals 1 over t squared from 1 to infinity. Okay, so definitely what I need to calculate over here is integral of from 1 to infinity out of t to the power negative 2d, which is equal to negative 1 over t, right? Because here this will turn into power negative 1 divided by negative 1. This is what we are getting. And now we've got 1 and b going for infinity. So now we get out of this that this equals to limit with b approaching infinity out of negative 1 over b minus, so because we have minus in front, this will be plus, and because it's 1, just 1. And now look, it's really easy to evaluate the limit here, because we see that as b goes for infinity, we are dividing 1 by a bigger and bigger number, so this expression goes to 0. And consequently, we can say that the area that we're trying to find is equal to 1. Okay, let me now demonstrate this on the graph. Okay, we will just use one part of the graph, the one that we need. And of course, we were looking what is happening from 1 to infinity. And we've calculated that this entire area below this function is equal to 1. Okay, so now let's try a different example, very similar, but where we get somewhat different outcome. So now, let's just say that I want to know what is the area below 1 over t from 1 to infinity. Well, seem very similar, but let's see what we get. Okay, so look, first, you just need to calculate integral from 0 to infinity, 1 over t dt. Here, of course, we use the logarithmic rule. Oh, I'm sorry, from 1. And because we know we don't get any negative values, we don't need absolute value. So over here we will have 1 and b going for infinity. So again, we calculate the limit with b approaching infinity out of ln b minus ln 1, which is simply 0, right? Now, how much is that? Look, natural logarithmic function looks like that. It grows slower and slower and slower, but it never stops growing. Which means that the limit of this expression is infinity. And look, even though the graph of these two functions, the one that we had previously and the one we had right now, look very similar. Actually, they do not they do not get the same result, right? Because we had area equal to 1, now it's infinity, which means that area cannot be calculated because the function is not convergent. So, in this case, we could simply show that this area is infinitely big. Okay, and of course, you will be practicing this quite a lot with Valeria during workshops, and once you get some familiarity with integrals back, we can start applying integrals to different economic problems. Okay, see you in the next video.